Have you ever made any hydrogen, Kristen?
No, but I've heard of it.
Yeah, okay. Well, let's make some. The hydrogen is locked up inside this chemical. It's an acid. And to get it out, we have to use these pieces of zinc metal. So put some in that jar.
Okay.
Okay. Now, carefully, very carefully, pour the acid in the jar. This is one you ought not to try at home unless your parents are around. Out comes hydrogen. That's enough. Okay. Now we'll capture it in this balloon. Okay.
Ah.
Okay, now let's let that cook there for a while and make some more hydrogen, but this time not so much. Come around over here. Here's some more acid in the test tube. So you put one of the pieces of zinc in the bottom of the test tube and pour a little of the acid on there. That's enough, that's enough, that's enough. See what's happening?
The hydrogen is...
It's coming off. Well, there's some water vapor here. Now light a match and bring it over there near the top of the test tube. Here, let me put it out with a card. Okay, now bring the match over there again. Obviously, the hydrogen is explosive, right? Okay, try another match. What you're really doing is combining the hydrogen with the oxygen in the air to make a chemical called H2O. You know what that is?
Hydrogen.
And oxygen combined, H2O, what's that?
Yeah. Well, it means...
Water.
Yeah.
Bring it over, right over the top. Okay, stop a minute. Let's let it cook for a while. Blow that out so you don't burn your fingers, and try one more. When you combine hydrogen with oxygen, you create H2O, water. Yeah. In fact, that's the basis for many of the scientists feel that eventually, when they're able to make hydrogen cheap enough, they will be able to compress it down into a liquid, put it into a tank, and you'd run your cars on it. A whole hydrogen economy, because there was no pollution. When you combine hydrogen and oxygen, you get water. Try it once more and make a tiniest drop of water. Ready? Go ahead. Get that. Okay. Blow it out. Let us now, what will happen if you bring a flame near a whole balloon full of hydrogen?
Will it blow up?
It certainly will. And first of all, I'll take the balloon off, and here's a string tied to a vise. It has a noose on it. So when I get it off, I want you to tie. Wait a minute, I'm going to tie a knot on it first. Okay. Now pull the noose nice and tight. Wait a minute, it's a slip knot. Push your finger up. There you go. Now, what'll happen when you let go?
It'll maybe go up?
Mm-hmm, because hydrogen is lighter than air.
Oh, neat.
Okay. Now, here is a candle on the end of a nice long stick.
Oh, no. I think I know what we're going to do.
You do? What?
We're going to get the heat from the candle close to the balloon, and it's going to blow up into water?
That's right. And we're going to make the tiniest little drop of water. Are you ready?
I think so.
Okay, go ahead. Go up there, touch the balloon. There you go. Here's a little puzzle for you. See, here's an ice cube, kind of what's left of it. It's sort of melted. And I'm putting it there in this glass of water, and I want you to use this string to take it out.
Well, I've read about it in a book, but...
Oh, you've read about it?
Yeah, but I've never tried it.
You've never tried it?
No.
Well, first of all, you're supposed to try to take it out with just the string.
Okay.
Kind of tough, you think? Try
Yeah.
it. See if you can pick it up.
It won't work.
Forget it, right?
It won't work.
So how are you going to get it out?
Well, first I need some salt.
Salt?
Yeah.
Plain ordinary everyday salt?
Yeah.
Okay. Salt.
Okay.
Now what do you do?
Okay. Then I sprinkle. Well, first I lay the string on the ice cube.
Right on top of it, right?
Yeah. And then I put a lot of salt on it.
Mm-hmm.
On the string and the ice cube.
Mm-hmm.
And then you have to wait for a few minutes.
Mm-hmm. Why, what's going to happen?
Well, the heat, well, it's going
First of all, why do you put salt on the sidewalk when it's icy?
to melt the
You know why it
Snow.
melts it? When the salt goes on top of the ice, some of it melts on the water on the top of the ice, and salt water freezes at a lower temperature than regular water.
Okay.
So that's why it melts it. But in this case, as the salt is dissolving in the water around the ice cube, it's taking heat away from the water that's in the string. So it's very important that the string be wet.
Okay.
So in effect, the water in the string is freezing it to the ice cube. That's the theory, right?
Yeah.
Okay, if that's the case, you think we've waited long enough?
Yeah.
Here is a string. Slowly pull it up. Let's see if what you did was correct. Ha-ha!
It's stuck on.
Yeah, it's stuck on. It actually froze on, right?
Yeah.
So now, even though you just read it in a book, now you've really done it.
Yeah. It's pretty neat.
Yeah. Can you recognize this portrait of a famous person? Leon Harmon at the Bell Laboratories wanted to know the minimum amount of visual information that was necessary to represent a human face. He scanned this well-known picture to determine the position and brightness of 1,024 points. He then divided the picture into squares and averaged the brightness value of all the points within each square. The result is what you're looking at. You can't recognize the familiar face because the information is too spread out. Your brain can't store the information from your eyes and make the identification. Now the camera's going to slowly back away from the picture, in effect bringing the squares closer together and the image within your eyes small enough for your brain to recognize the portrait of the famous person, reduced to the minimum number of squares with a computer. Watch how the image becomes clearer and clearer as it becomes smaller and smaller.
Geyser, a natural spring or fountain which discharges into the air at more or less regular intervals of time. A column of heated water and steam.
Yes.
So now I know what a geyser is.
And turn the page here. There are pictures of geysers from all over the world. Here's my favorite. That's called Old Faithful in Yellowstone National Park. Shoots water 50 feet in the air. And I have one in the kitchen, too.
That's impossible.
Well, you think so? Well, I'll show you.
But you can't have a geyser. It goes too high.
Oh, you mean 50 feet in the air like Old Faithful? Well, I wouldn't want one that went that high. You know, I'd get the ceiling all wet. And this is a Faithful geyser. But a geyser doesn't have to go 50 feet in the air. It can sort of bubble up. And that's what this one is doing. I remember what it said in the encyclopedia. Heat of the earth below, right? Well, we have a stove heating up the water. Water that's being changed to steam. In this case, there's a funnel in there. See how you can see it in the middle of the beaker? That's collecting all the steam. And when there's enough pressure inside, the water that's in the stem is pushed out, bubbles over the top, and that's a geyser. Now, here's the one you might have in your kitchen. How do you make coffee?
By a drip coffee filter?
A filter.
Yeah.
Well, this is called a percolator, and there's another way of making it, and is the geyser most people will have in their kitchen if they have one. So they're both the same idea. You go ahead and trace what happens there.
Okay, they both have hot water, and the steam collects together and goes.
In this case, there's a plastic funnel down there.
Yeah,
so
the plastic funnel, and it goes up through the plastic funnel, and the water's in there, which goes up the dome, which the water squirts out, which looks like a
because there's
bubble.
water in the stem, right?
Yeah.
And it pushes it up. And that's not really a bubble, that's the hot water coming out, and it looks like. Now, they call this a percolator, not because it bubbles like this. The word percolate means to seep through or slowly go through something. This hot water seeps through the coffee grounds, which are ordinarily in that little basket, and drip down here. So then it gets boiled over again and comes up here and continues to circulate round and round. So anytime you see one of these, they have a geyser in their kitchen.
I'll tell my friend that.
Okay. And you'll be able to explain it?
Yeah.
Okay, good. Here's a balloon filled with water. You take it and put it in the bottle.
Okay. Won't fit. It won't go in because it's too big.
Right. I made it too big purposely. Well, you and I are going to get that balloon inside the bottle. But I just thought, have you ever heard of a milk bottle?
I've heard of it, but I've never seen one.
How do you like that? Because that was the famous experiment that probably is more famous than any other experiment, was how to get a hard-boiled egg peeled into a milk bottle. Well, this is a sort of modern version of it, and that's the reason I use a balloon filled with water, because you can make the balloon just big enough so it can't go in. Now, here's the way it was done with the old egg in the milk bottle business, and we'll do it with a balloon. You take the balloon, I'm going to set this piece of paper on fire and put it inside the jar, and then you take the balloon and put it right on top.
Okay.
Now, with the paper inside burning, what's going to happen to the air?
It'll expand.
Right, because we're heating it.
Yeah.
Okay, but it can't get out any place except
The top.
right up
At
there.
the top, yeah.
So it'll bubble out. Okay, then it'll settle back down again. Now when the fire goes out, what's going to happen to the air?
That'll sort of like drop in. Drop in.
First of all, the air is going to shrink, right, take up less space because it gets cool, and the outside air pressure pushing all around here is going to push the balloon in. Okay?
Yeah. Okay.
All right, so you get ready. You do this at home. Be sure and do it with your parents or an adult of some kind, because it's fire, and you don't want to be fooling around with fire. You ready?
Yeah.
Here we go. That's all there is to it, just like that.
But it didn't bubble.
There it is.
Now you got a problem.
What's that?
Can't get it out.
Well, there are a couple of ways. A handy tool is an ice pick. You know, you go in and jam the balloon and break it, which wouldn't be right. Well, let's just do the reverse of how we got it in. To get the balloon in, we lowered the pressure in here, didn't we, by making the air expand and then cooling it. So to get it out, all you have to do is tip it around like this. See if I can get rid of the paper first. If I can get the air pressure greater back here, that'll help pull it out. And here's how you do it. Get the balloon like this and blow. And if I blow real hard and then pull on the balloon, that'll act as a one-way valve going in the other direction, and I should be able to get it out. Watch. Just like that. Okay, you think you can do it at home?
Yeah.
Okay, good. These are germs that could be inside of you right now. With time-lapse photography, they're multiplying faster than normal, but it's been estimated that inside of every human being, there are more bacteria than all the people who ever lived. If you can't escape from germs, why aren't you sick all the time? Here's one answer: the white cell on the right. Inside of you are millions of white cells that attack germs like the one on the left. If the white cell wins, you stay healthy. If it loses and the germs begin to multiply, reserve white cells by the millions pour forth from the marrow of your bones to attack the invaders. How does a white cell kill a germ? Well, the mystery was solved by a team of scientists at Rockefeller University, headed by Dr. James Hirsch. He shot these motion pictures through the microscope at magnifications of up to 1,500 times to see what was going on inside of the white cells. By examining individual frames of the film, he was able to piece together how a white cell kills a germ. He saw that a white cell can sense that a microbe is nearby and move toward the germ. It begins to engulf the microbe like this and eventually surround it. The germ is held in a pouch inside of the cell. The black bodies next to the pouch contain powerful chemicals. They fuse with the wall of the pouch, discharging the chemicals onto the germ. The germ is killed, and eventually digest it. You're never completely free of germs, so somewhere inside of you, this same battle is going on right now to keep you healthy. One of your defenses against disease, your white cells. You recognize this, Tanis, don't you?
Yes, it's a paper tube. It's a cardboard tube from a paper towel roll.
Yes. Okay. Would you take this piece of what?
Tissue paper.
Put it down and smooth it all around the edge of the tube. Because I will then take this rubber band and put it on like that. So the end of the tube is now covered with tissue paper. I would like you to take this piece of broomstick, push it in like that, and you think you have enough strength to push it right through and break the tissue paper?
Yes, I do.
All right, try it. Very good. Now we want to do the same thing again. Everything exactly the same with one small change. We are going to add some strong salt to the tube.
Strong salt. Is that any different from regular salt that you eat?
No, it's the same old regular salt, but it's a lot stronger than you think. Here's the tissue paper. Put it down over the...
Okay.
Get it all folded around there. Okay. Put it on just as before. Here comes the salt. A couple of inches or so, right?
Yeah.
All right.
There.
Now, this time, put the stick in like this and push down as hard as you can. Break the tissue paper.
Okay.
Think you can do it?
Well, I don't know. Maybe.
All right. Go ahead, try.
No, I can't do it.
It seems strange. Why? Why can't you push it, go right through the tissue paper?
Because the grains of salt are so small and they don't have enough pressure at the bottom to break the tissue paper.
That is true. They don't have enough pressure, but that still doesn't quite explain it, although you were close, because you said they were so small. When you push down on it like this, instead of the pressure just going straight down, it also goes sideways. So you're really pushing against the side of the tube.
Oh.
And the harder you press, the more they go in all directions, you know, including down, and that's why you can't break through the tissue paper.
Oh, but if you pushed hard enough, wouldn't the cardboard tube break?
You can't push that hard. I can't push that hard. That's how much, because you're putting it over this whole area where all the salt is.
Oh,
Now, have you ever
I
seen
see.
a pile driver? Remember it piles big poles like that into the ground?
Yeah, I've seen that on TV before.
Well,
yeah.
this is the principle of the pile, because when they take a great big telephone pole-like thing, pound it into the ground, the pressure is going in all directions in the ground, just like this. They can build a whole building on top of it. Let's make sure that you still have your strength. See if you can do it now.
Okay.
Very good.
Thank you.
Can you describe a circle for me?
Well, it's rounded, and it doesn't have edges sticking out.
That's sort of like what rounded means, right?
Yeah.
No bumps.
Yeah.
Well, can you draw one for me? Here, I've got the compass all set up for you. You draw a circle.
Oops.
Okay. Now, I made that compass just the right length so that when we put this piece of cardboard down, that's one what? Diameter.
Diameter, yeah.
Measuring the distance across. If you put the piece of cardboard going this way, will it be longer or shorter?
Same.
Yeah, of course. What about this direction?
Just the same.
Okay, so one definition of a circle is a figure that has equal diameters
Yeah.
in all directions, as long as you go through the center. Okay. Now you can see why, come on around over here, you can see why people, when they want to move a heavy refrigerator or a house or something,
Yeah.
they put underneath it what?
2 round objects.
Yeah, rollers like that. These happen to be rolling pins. Okay, now put your hand on there and run it back and forth. Why doesn't it go bumpity bump?
Oops. Well, because these rolling pins have equal diameters.
Right. Same distance from the table up to the bottom of the board all the time. Okay, now come back over here. Could you think of any kind of figure in which they have equal diameters, but it's not a circle?
Oh, no.
Most people can't. The only figure that most people can think of
It's a
automatically when you say equal diameters is a circle. Well, there's a whole family of geometric figures that are not circles, but have equal diameters. There's one of them.
Oh.
Now, I made that circle the same size as this. You take the cardboard and measure from that bump up to here, right through the center.
It's exactly the same.
Okay, now go this way.
It's the same as this
Yeah,
one.
it's that. And now give it to me over here. Look, over there.
Yeah?
Equal diameters in every direction.
I thought only the
Yeah, a circle could
was.
do that.
Yeah.
Now, if we take these and put them under the board over here. Here, just put those down there on the shelf. Looks like when they roll, look, lump, 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 right? Okay, put the board on top. Okay, now gently roll it.
It's just like the
Just
rolling
like
pins.
yeah, just like the rolling pins, except this time you're using these funny little shapes. So the next time somebody ever would challenge you about a circle is the only figure with equal diameters, you can now say, oh no, there are other curves of constant width.
Curves of constant width.
Right. Shannon, can you read that for me?
No, the letters are too long and they're too skinny.
Yes. I did them that way purposely because I wanted to remind you that you are so accustomed to reading letters of a certain height and a certain width that the minute you make them in this long perspective, you can't read them at all.
Yeah, I guess.
Have you ever seen long letters longer than they're supposed to be?
Well, yeah, on the street.
What happens?
Well, you see, when you're driving along, you can see them from a distance because they're flat.
Well, they're flat. Now, but when you go out and look at them straight down
Yeah.
like this, they're real long. Okay.
Yeah.
Okay, now, then in order to read this message, I will turn it so that you're looking at it long like that, just as though you were driving along in a car. Okay, are you ready?
Yeah.
You call it out the minute you can read it. You can close one eye, that helps
Okay.
too. Okay, here you go.
The last experiment.
The last experiment.
Experiment.